Hey guys, all right, let's go through our textbook. I know it's been a long time coming. So I'm going to start on page 406, and let's look at this paragraph right here at the bottom. This is excellent Friday quiz information that we've talked about. So we're going to highlight the words solar system, star, star cluster, galaxy, galaxy cluster, and supercluster. So on your Friday quiz, you're going to need to be able to do like a matching game. So if I say, what is a large-scale structure and consists of at least one star? You would say solar system. If I said made up of hundreds of galaxies, you would say supercluster. So kind of definitions and kind of like a hierarchy, like which one's the smallest, and then work your way up to which one's going to be the biggest. All right, so read that section. Moving on to the pictures. I like this picture. This is the easiest one to start with. So I see that I've got a planet. Looks like it has an atmosphere and a thin blue layer, so it might be Earth. You can almost see something that might look like a moon. And then here's obviously a bright star. So if we've got a planet, perhaps even a moon, orbiting a star, then that's going to let me know we have a solar system. The next easiest one for me to figure out is definitely this picture of a galaxy. And if you notice, it's got that brown reddish tint to it, probably taken with an infrared image. Okay, moving on to this one. You see these bright, sparkly stars and what looks below here like a nebula or a forming star. So then we've got a star cluster for D. So it looks like alien spaceships that might be glowing. These are going to be left with our galaxy cluster. So A, galaxy cluster, B, solar system, C, galaxy, and D, star cluster. All right, on these pages, we've got some scientists, absent the women, of course. So let's look at these guys, though. So I'll try to highlight so you can make sure to see it in the video. So first we'll start with Isaac Newton. These are not going to be on your Friday quiz, but it is neat to talk about these scientists and to talk about, I guess, the history of all of our scientific discoveries. So it's neat to see the progression from one generation to the next. So Einstein, law of gravitation, his idea was that the stars were fixed in one place and that they were spread out evenly through the universe. So that's kind of unique because we're going to come back to talk about this and if that was right or not, or if we had to adapt some of our ways of thinking. Moving on to Einstein, theory of special relativity. So that's the first one. And it explains how gravity causes space and time to curve. He also had the idea, his studies would show that the universe was expanding. So this was the first time we're starting to think that maybe our universe is getting bigger. Because Newton thought everything stayed in one fixed place. Then we start to adapt to think maybe the universe is expanding and moving away from each other. Again, they're just ideas, because you have to wait until this guy before we start to get some mathematical explanations. So I'm not going to try to say his name. I don't know. Lemaitre maybe? So we're going to underline right here that he explained the relationship between the distance of galaxies, and I've also circled distance, and the speeds at which those galaxies are moving away from Earth. So let's do some extra attention to the word distances and speeds. So now we're realizing that these galaxies are moving, and they're moving away from where we're at. So he thought, he proposed a hypothesis that was later developed into the currently accepted theory of the origin of the universe. So this was some of the first work that we did for Big Bang. So he thought that if the universe was expanding, all matter must have been packed into a small space. So that could have been our origin. All right, and then we've already started our study about Edwin Hubble. So first scientist to present some actual observable evidence to support the idea that the universe is expanding. So we had the idea over here. Well, we didn't have the idea here. Then we have Einstein giving us the idea that maybe the universe is expanding. We have Lemaitre, if I'm saying that right, start to put some math behind the theory to give us that all matter was maybe created in a very small space. And then we've got Hubble giving us this observable evidence. So I really want you to focus on those words. Observable and of evidence that the universe is expanding. And we've already started our talks about red shifting, and that depends on the distance from Earth. Okay, and then the last guy, George Gamow, don't know if I'm saying that right either. So this is the guy to outline the theory of how elements are formed in the universe. He knew that most of the visible matter in the universe was going to be hydrogen and helium. So if you did your star spectra gizmo, or if you're going to do the gizmo, you'll notice that a lot of the stars are going to contain hydrogen and helium atoms. And then he also talked about how elements were formed. All right, so moving on from our scientist study, we're going to come over here to our evidence for the Big Bang. So what is the evidence that scientists use? We've highlighted these in class. So we're going to say number 1, the abundance of light. Number 2, the red shifting of galaxies. And 3, the cosmic microwave background. And so I'm going to take a little section in my book right here, and we're going to remind ourselves that we say CAR to remember that, if you can see that. So C stands for the CMB, the cosmic microwave background. A is for the abundance of light. We cannot say this enough. It will be on your test. Of light. And R for the red shifting. So abundance of light is pretty self-explanatory. So the theory predicts a certain percentage of light elements in the universe, and they are supported by data. So I don't know that we can say that enough in science, that the predictions are supported by data. So the abundance of light elements in the early universe can be compared with the abundance of light elements in the stars today. So how they do this is that they study stars that are very far from Earth and in the early stages of development. Scientists analyze the spectral lines. So that's going to be like those gizmo images that you saw. They look like this up here in the corner. They analyze the spectral lines of these stars to determine the amount of elements being produced within the core of the star. The percentage of light elements in these stars are very close to the theoretical values predicted by the Big Bang Theory. So we're trying to take those theories, and more often than not, they're trying to disprove them, and then sometimes they end up finding evidence to support the theory. So redshifting of galaxies. I'm just going to move on down. So the redshift show that the galaxies are moving away from each other, shifting to the red side. So if you weren't here when we had a chance to go over this, follow these little lines right here. I'm going to stop and take a minute to talk about how we see colors. So if you saw this in class, you can fast forward a little bit. But let's take my purple pen, for example, favorite color. So how do I know that this pen is purple? How do I see purple with my eyeball? So this is really good Google and YouTube material to go look this up. We will spend some time in class when we talk about light waves to talk about how we see colors and the waves that hit our eyeballs. So when our lights are on, I'm going to show you them in my classroom. So let's look up here. We've got the lights on. What color is coming out? Oopsie. Yeah, am I still recording? Okay, so what color is coming out of these lights up in my ceiling? That looks white, doesn't it? And there's Einstein on the wall. Hey, dude. All right, so when we look back down at the book and we look at my purple pen, if I have a white light hitting my purple pen, what colors make up white light? Well, we talked that all light, white light, is made up of all colors. So if you've got a prism and you put that prism on the table and you shine the light through it, it's going to divide that light into the electromagnetic spectrum, or the visible light spectrum, going from red, orange, yellow, green, blue, indigo, violet. So that's Roy G. Biv, except that these are backwards. That's how we remember the order. Red, orange, yellow, green, blue, indigo, violet. So coming out of those white lights in the top of my classroom are all of these colors. So all of those colors are hitting my purple ink pen. Some of those colors get absorbed by my purple ink pen, and some of those colors are reflected by my purple ink pen. So all of them get absorbed, but what is bouncing off this purple ink pen to come back to my eyeballs? The purple would be. So all colors hit the pen, and then all of them are absorbed except for the purple color, and that's what makes a wave all the way back to my eyeball so that I can see the purple color of this pen. So we'll get into that a little bit more, but that's what's happening when we're looking in the solar system, and we're going to see that if you see these black lines, in the textbook on our spectrum, this is a spectrum right here, that square. I'm going to make these a little darker for you. So if you see these lines, what happens in the second one here? All of these lines, they're in the same place, but they've moved which direction? They've moved over to the right, over to the red side. So they call that red shifting. So just like the FBI has fingerprints that they put in a database of criminals, so that anytime you have a fingerprint, you know, I can pick up this marker, there's going to be a fingerprint on it. I can send that fingerprint to a lab. They can run it through a database and compare my fingerprint to every single other fingerprint that they know of. And maybe they'll get a match, and they'll be able to compare those two fingerprints to see if they're the same. So we already know, scientists already know what the spectrums look like for every single element in the universe. So we can compare those spectrums to what the light spectrum looks like coming from an unknown object in space. And then when we do that, we can say, oh, okay, this might be hydrogen or helium or whichever element. Then we can start to compare, I know based on these lines which element it is. Then I can compare if those lines have shifted to the red side or if they have shifted to the left side. And then that tells me something about how that object is moving in relation to where we are. So that's kind of complicated. We're going to be on this for a long time. But I do want you to know that the star, the gases on the atmosphere of the star, are releasing all of these colors. So they're being released, except for where you have these lines. That's the part of the spectrum that's being absorbed by the star. And we can't see that. So there's information in what we aren't able to see, and that tells us things. All right, moving on. Cosmic microwave background, CMB, the C to our car, so that we can remember that. So there was a couple scientists. There was a good podcast I was listening to. That's what all good stories start with. And these guys, I think this was in one of the videos that you were watching, the Ed Puzzle, about some of the telescopes that they had made. So they took their telescope and they pointed it to a part of the sky where there was nothing at. They knew there were no stars. There wasn't anything there that should have sent back any kind of wave information, right? Well, they start getting feedback. They get some radio waves. Okay, so they think, well, maybe there's a problem and pigeons had built a nest. So they cleaned the pigeon stuff out and they thought maybe that was interfering with our telescope, sending us bad information. So then they did it again. Well, they got the radio waves back again. And they're like, this can't be right. There's got to be a problem somewhere. We know this is a part of empty space where we should not be getting any kind of waves coming back to our telescope. Okay, so they move it to a different part of the universe where they know there's nothing at. They're trying to point it at black space, and they're still getting radio waves back. So that was one of the first times that we started to realize that there is radiation in every single part of our observable universe. Anywhere that you want to point a telescope at, you are going to get feedback in the form of radiation. So that's what this map is telling you. So this sky map was made by NASA's WMAP mission, and it shows that the temperature of the cosmic microwave background is increasing from dark blue to red. So a small temperature difference can indicate some of the first major structures in the universe, such as galaxies and superclusters. So that's going to be your answer to 13. What can you see? Well, you can see some of the first structures in the universe. So why would there be radiation in every small little square inch of our universe? Something had to produce that radiation. So that's another piece of evidence for the Big Bang, because that radiation had to get there from some kind of nuclear explosion. All right, moving on. So page 412 and 413, we decided that we were not okay with them trying to replicate Big Bang inside a chamber, and we at least didn't want to live close to it. So that's what they're doing here. So what were the conditions of the early universe? Let me find my highlighter. So the universe was no bigger than an atom, and it was extremely dense and hot. We're going to leave it right there, and we'll come back to some of that a little bit later. So number 15, it goes on to talk about that scientists use particle accelerators to model the conditions in the early universe. So particle accelerators to model it. So data from experiments have provided evidence of the particles that first existed in the universe. So you could even use this as a piece of evidence, but that's not something that we're going to add to our collection that we're going to study more in depth, but that's some more information for you. Scientists are also trying to find out how those particles combined to form the different atoms. All right, so 15, how does a model of the Big Bang differ from the actual event? Well, we decided that it's definitely going to be smaller. And that it's probably not going to be an exact replication due to the scale is just not as big as it was for that. All right, so let's look at how scientists estimate the age of the universe. So I want to point out this picture here, and you probably can't see in my video, but if you look at your book, you can see that you've got the sun in the same place, or whatever's in the middle. I don't even know. But if you look at the objects, as it gets bigger, are we including more objects, or are they just spreading apart? Yeah, they're just spreading apart so that there's more space between everything. All right, so you can use the speed of a car to determine the time it takes for the car to reach its current position from the starting point. So estimating how long it's going to take you to get to Florida. So scientists can also estimate the age of the universe by using the present rate of expansion of the universe. So if I know that you're driving 70 miles an hour now, and I know that you're going to drive to Florida at an average speed of 70 miles an hour, we can predict when you would get there. So if we know how much the universe is moving now, we can just reverse engineer that and figure out how long it's been doing that, right? All right. So they measure how fast galaxies are moving away. How fast they're moving away. So it sounds a lot like that Lemaitre, some of his math that we were talking about when we looked at the scientist. And current data show that the rate of expansion is increasing or accelerating. They use the present rate of expansion to estimate past rates of expansion. So in science, if it's happened once, it's going to happen again. And if we can look at trends and patterns, then that helps us find out all kinds of information. Helps us kind of backtrack our story here. So for number 16, instead of me reading it to you or rewriting, we're just going to zoom in right here on the answers. So there's your 16. The rate of expansion indicates how fast objects are moving away from Earth. Based on that rate, scientists work backwards to determine how long ago the galaxies were clustered close together. And then this would give us an estimate age of the universe. So if you need to pause that, go ahead, but I'm going to go ahead and move on. Okay. All right, so we did our review at the end. I'll speed through this one. All right, so here we have a picture. What is made up of many galaxies? A supercluster or a solar system? Yep, that would be a supercluster. I don't want to mark these in my book, so I'm going to let you see the answers a little bit down below. How about I just do that? So 17 is going to be a supercluster. 18, who was it that let us see observational evidence that supported the concept of an expanding universe? So that would be our Hubble with our Hubble telescope. So hopefully that's really something that you're confident in doing because we've talked about that a lot. Number 19, Big Bang Theory is supported by the abundance of what? Heavy elements or light elements? Yes, it would be light elements. And if you answered number 20 is not required. But if you answered that, you would summarize how all of those four scientists contributed. So you could start back and say they had the idea, then they figured out the math, then we figured out how to look at it with a telescope. So that was kind of the progression there. All right. So here's going to be your answers for the other ones. This is number 1. According to the Big Bang Theory, the universe began as a tiny volume that suddenly and rapidly began expanding. Number 2, CMB is the remnant of the early radiation that filled the universe. Number 3, the universe is all space and all of the energy and matter in it. Number 4, a redshift is where you shift toward the longer wavelengths of light when an object is moving away. I'm just going to tell you number 5 is B. You guys go check yourself and see what that was. Number 6, who was looking at the elements, discovering hydrogen and helium formed in the early Big Bang? That would be George Gamow, the very last one. Number 7, it was Lemaitre, that used calculations to show universe is expanding. Gotta love that math, right, guys? Number 8, it's asking about a map of the cosmic microwave background and how we see that radiation. So it shows all of the radiation left over from the Big Bang, that it fills the sky. There is not anywhere you can look and not see radiation. They haven't found a place yet. So for number 9, what evidence other than the CMB provides support for Big Bang? So we're going to go back That was our C, so we're going to talk about the abundance of light. So C for CMB, A for abundance of light, and R for redshifting. So you can remember car, like the Back to the Future car. That's our little trick for this part. And then for the last one, number 10, Newton's law of universal gravitation describes how the force of gravity depends on the mass. So force depends on mass. And then the distance between the objects. And that helps scientists explain why solar systems form and why objects are held together in galaxies. So we'll get into gravity a little bit more. We'll have a couple weeks where we just talk about gravity in the universe. And that's your bookwork. Thanks, guys.